Good morning all. Today we are going to discuss about vulcanization and Cure reactions. First of all, we are going to discuss about vulcanization. Vulcanization, it is a process by which a network of crosslinks is introduced into an elastomer, and it is discovered by Goodyear in 1839. It transforms an elastomer, that is, for example, an rubber, from a weak thermoplastic mass without useful mechanical properties into a strong, elastic, tough rubber. Vulcanized rubber have more uh, good physical properties than that of an unvulcanized rubber. In this figure, we can see a molecule of rubber or any other molecule before vulcanization and after vulcanization. And below we can see the process through which a natural rubber is vulcanized, in which the monomer, that is the isoprene units, are being linked by sulfur bonds. In this figure we can see the stress strain curve to 600% elongation and back, typical of unvulcanized and vulcanized natural rubber. In this figure we can see that vulcanized rubber is more elongated than that of an unvulcanized rubber. It shows that vulcanized rubber have a greater good physical property or greater elongation than that of unvulcanized rubber. These are some of the items that is vulcanized. Here, rubber can be vulcanized or cured without heating by the action of sulfur chloride. A large number of compounds that do not contain sulfur can vulcanize rubber. These can be categorized into three different groups. They are oxidizing agents. We can give examples of oxidizing agents as selenium, tellurium, organic peroxides, nitro compounds, etc. Second is generators of free radicals. Examples are organic peroxides, SO compounds, and many accelerators. The third category includes phenolic resins. In this figure, we can see some of vulcanization initiators like benzothiazole 2-thiol, dithiobis morpholins. These are important to initiate a vulcanization process. Next is accelerators. These are also an important substance that is involved in vulcanization process. Mainly, vulcanization takes place by heating in presence of sulfur alone. But this process is relatively slow. So, we need a process which can be commercially used, and it should be faster enough. So, in order to speed up many fold by the addition of small amounts of organic or inorganic compounds, and these are known as accelerators. And many accelerators do not work alone. It requires certain presence of other chemicals, and these chemicals are called activators or promoters. Activators are usually metallic oxides such as zinc oxides. These speed up the reaction many times faster than without it. And thus we can conclude that vulcanization requires sulfur, organic accelerators, a metallic oxide, and a soap for its effective processing and to obtain a quality product and to get a good yield. Next is chemistry of vulcanization. Sulfur vulcanization. The curing of rubber with sulfur alone is quite slow. Mechanism predicted for this process is free radical and ionic intermediate. Typical accelerator for these reactions, that is for sulfur vulcanization, are thiazole. Example is 2-mercaptobenzothiazole. Next is dithiocarbamate. And third is amines. Next, there are also retarders like N-cyclohexyl thiophthalimide, which has proven very effective in inhibiting premature vulcanization. In the process, the accelerator reacts with sulfur to give sulfides. That is, accelerators first of all react with sulfur, and it break the sulfur molecule and gives a sulfide linkage, and these polysulfide then interact with the rubber to give intermediate. These further with the final crosslinks being of the general type that is given in the figure below. We can see a cross-linked polyisobrin chain in this figure. The role of zinc oxide is which produces zinc ions in the presence of fatty acids, appears to form chelates with the accelerators and sulfides, retarding and thus smoothing the course of vulcanization. That is, the role of zinc oxide is mainly to form chelates with accelerators and sulfides and smoothing the process of vulcanization. The double bond in the elastomers are not saturated in this mechanism but contribute by enhancing the activity of the allylic hydrogen at which the cross-linking takes place. Next is non-sulfur vulcanization. In this process, a free radical R is formed by the decomposition of or of oxidation of curing agents or as a step in the oxidative degradation of rubber. Next, the free radical initiates vulcanization by abstracting a hydrogen atom from one of the alpha methylene group. That is, in a rubber monomer of a natural rubber, we can have an alpha. We have an alpha methylene group, and in which the free radical abstract hydrogen from this group. The rubber free radical then attacks a double bond in an adjacent polymer chain. The result is the formation of a crosslink and the regeneration of a free radical in a reaction analogous to propagation in an addition polymerization. Next is termination occur by reaction of a rubber free radical with a free radical fragments of the curing agents. The termination reaction between two rubber free radicals is considered because of the low probability of two such radicals coming into position to react owing to the high viscosity of the medium. Next, we are going to discuss about Cure reactions. Cure reactions is also like vulcanization, where we form a crosslinks, and Cure reactions also lead to cross-linking. These uncross-linked linear polymers contain either reactive functional groups or double bonds in a molecule. That is, uncrossed molecules, linear molecules have certain reactive functional groups or double bonds. They are usually not of a very high molecular weight and in the form of liquid resins. Such liquid polymers possessing reactive functional groups or double bonds are referred to as prepolymers. That is, these reactive functional group containing groups are called prepolymers, and these are important reactants in a Cure reactions. When these prepolymers are reacted with a low molecular weight or polymeric substance containing appropriate functional group capable of reacting with active groups of the prepolymer, curing takes place, resulting in cross-linked solid polymeric mass. And these these prepolymers react with a curing agents. These curing agents is a low molecular weight polymeric material. These are very low molecular weight polymeric material. For cross-linking to take place, both the prepolymer and curative should not have a minimum functionality of 2, but one or both of them should have some trifunctional molecule also. That is, when the reaction takes place between curative and the prepolymer, at least one of them should have a trifunctional group or both should have a trifunctional group. Linear coupling will result only in another linear molecule of a longer chain length. The amount of cross-linking depends upon the ratio of the bifunctional to trifunctional molecule present in the system. Next, we are going to see some of the examples of Cure reaction. Here we can see the curing of an unsaturated polyester resin using styrene and a free radical initiator. Here the prepolymer structure is shown, and the curative is a styrene molecule, and the reaction is shown below. We can see the cured network structure too. Next is curing of thiol terminated polysulfide resin with PbO2. Here, prepolymer structure and curative is given. The curative used here is PbO2. Yes, we can also have so many examples of cure reactions. We have only discussed two of them in this slide. I hope you understood what is vulcanization and cure reactions. So, thank you.